the 2024 IEEE 9th International Conference on Engineering Technologies and Applied Sciences, ICETAS. Today, the title of our paper is Characterization of Passive Circuit Elements Using Resonant Circuit Techniques for Wireless Communication Applications. And our paper ID is 497. The authors of this work includes Abdulwahab Deji from Whitsom University and a whole lot of other authors. Now let's go to our work, today's work, and this is presented by Prof. Dr. Abdulwahab Deji. Now, in this regard, we first of all look at the introductory aspect, and in this introductory aspect, we took a look at the overview of the problems and the objectives of why we are doing this research, the problem we have identified in literature, and the objectives that have motivated us to carry out this research. The first part of this is the importance of the passive circuit element. The passive circuit element has found wide applications and usage in electronic circuitry. And in our case, we make basic use of the resistors, the capacitor, and the inductors of the which are passive circuit in creating a resonant circuit, and which has enabled us to create an ability to transfer energy and power wirelessly without contact. So the whole essence of this design is to create a system where we can carry out measurement without contact, without physical contact. So it's like we're creating a sensory system that can carry out measurement using a passive circuit element to create a resonant circuit in power transfer applications and in pressure sensor applications. Okay, so the overview is all on the resonant circuit techniques that we've used. The resonant circuit techniques is what we use, and the devices we use to model this resonant circuit are the basic passive circuit elements. Okay, now let's take a look at the problem statement, the challenges we found in our the problems we found that we identified and motivated for a solution, that called for a solution. Now, one of the challenges we found was the difficulty in accurate non-contact measurement of passive components, other DC bias. So we found a lot in literature that still there are a lot of difficulty in carrying out non-contact measurement anytime we're using passive circuit component or passive circuitry, okay, in a DC non-biasing system. Another problem or challenge we found in literature is the existing method actually failed to optimize high frequency performance and energy transfer, wireless energy transfer. So to have a wireless power and energy transfer, we need to optimize or create an optimization that can catch up with the pace of today's electronic circuitry. So why does this research matter? One of it is the essential for the design. One of the reasons why this research is very important is that it is essential for the design of efficient wireless communication and power system. So if we want to have efficient and effective and high efficacy wireless communication and use in electronic circuitry and power transfer system in electronic circuitry, using passive circuit elements such as inductors, resistors, and capacitors, we're able to model a resonant circuit that can help us carry out non-contact measurement. Another reason why this research is very important is the need for the techniques ensuring minimal harmonics distortion and high efficiency. So the need for a new technique to ensure harmonics are very at minimal and there's high efficiency in the system, like we have obtained in this regard. Now, a quick review of the literature is that we looked at some existing literature as we've highlighted, reference 2, reference 3, reference 4, the most pragmatic ones, reference 4, reference 8, reference 9, reference 12, that we've looked at. We are able to harness the importance of resonant circuits in analyzing the passive components. This one obtained from reference 2 and reference 3. So here we're able to, a quick look at the state of the research is that we're able to harness the importance of the resonance circuit. And because we're able to bring out the importance of resonance circuit, we're able to analyze the passive component, the role they will play in developing a resonance circuit that can do the non-contact measurement, as the case may be. Now, another important part of the literature review, that summary of the review we've done, is the previous work on inductors and capacitor modeling. So we've looked at the previous work that has been done on capacitive measurement and inductive measurements and the modeling of this type of circuit. Another area we've looked at in developing our system is the limitations of existing approaches in real-world application, the limitations that are there in the already existing applications of resonance circuit that are already in existence, the various applications in measurement, in temperature measurement, pressure measurement, and every other applications, the existing problems, we have looked at them, and the limitations that this research have on this area, we've looked at them, and we summarized them. And the basic reference are 9 to 12. Reference 9, 10, 11, 12, we have summarized the real-world challenges and the limitations they have on the existing system. Now, let's take a look at the key gap that we've identified. One of it was the lack of a comprehensive approach for impedance and resonance frequency characterization. So there was no comprehensive approach as of today that has been developed for the impedance and the resonance frequency. So characterizing the resonance frequency, other different adverse conditions has not been obtained even up till now. So one of the gaps we created and we harnessed the opportunity to solve this problem was the lack of a comprehensive approach for impedance. So this research has addressed the impedance problem, the impedance matching, the normalization, the standard normalizations of the impedance from this resonance circuit and resonance frequency obtained for various adverse conditions. Now let's quickly take a look at the objectives. Now we have the primary goal already because we already know where the problems and what are the objectives, the aims that we put in place in order to solve these objectives. The first one was to develop a resonance circuit-based technique. So remember, the whole objective is to develop a resonance circuit-based technique for what? For characterizing passive circuit elements such as resistors, capacitors, and inductors. So the big objective was to develop a resonance circuit that finds other applications for power and energy transfer across board in the system. So this was the big objective. But the specific objective, the big goal, the specific objective was, one, to achieve high measurement accuracy with minimal harmonics, very high and accurate measurement accuracy, very high and accurate and precise measurement with minimum harmonics. This was the first objective. As we have these challenges still in the existing literature, okay, that's the first objective. The second objective was to validate the methods through simulation at various power level. So to use simulation to see if the system is good enough to go, is good to go. So simulation was used to validate the methodology that we are adopting, or the improvement that we brought to the existing literature at various power levels, because the applications of this research is to transfer power and energy across a wireless gap, across a gap. The third objective was to optimize the energy transfer for inductive wire communication. In fact, this was the application of the research. The application was to transfer energy and power wirelessly for telecommunication applications. Now let's quickly take a look at the methodology we use, the method we use. The first one was, let's look at the approach first. Approach to how these problems were solved. The first one was the analytical modeling of the inductive wireless power transfer. We did the mathematical modeling of the wireless inductive power transfer. And then the next step in the method we used was to design and simulate the resonance circuit itself. To design and simulate, okay? The third methodology or the third approach we used was the characterization of impedance, voltage, and current gain. Here, after we design and simulate the resonance circuit, we characterize the impedance, the voltage, and the current gain in this regard. Now, here are the key steps that we follow. The input excitation phase, okay? Remember, this system comprises of three phases. The input phase, the processing phase, and the output phase. Now, the input phase is the excitation phase. Okay, this is where we let in power into the system, and the processing is done. The processing is done in the second stage. So the input stage is just where we let in power into the system. And now this phase comprises of the configuration of the series and parallel resonance circuit in our case and in our application. The second phase is the processing stage. In this stage, what we did was to analyze the inductive complete system that we developed with mathematical method. Okay, is to analyze this phase is to analyze the inductive complete using mathematical techniques. The third phase was the output measurement, where the measurement is taking place across the gap and the transfer and the applications. So here we were only validating the performance of the experimental result that we got in the output. Here are some of just few basic mathematical equations that we use. The resonance circuit is a well-known resonance frequency. It's a well-known formula that we try to arrive in our modeling. Now, the primary and secondary impedance we obtain in series and in parallel. These are just the basics. Most of the equations are in the research paper itself. Okay, now the equation for the voltage and the current is given as the voltage gain summarily, and the current gain is given. The standardized current gain equation is given below. Okay. Now let's look at the model itself, the inductive power transfer system. So here is the system. We have port 1, we have port 2, and we have the coupled loop. Okay, so we have port 1, which is the inductive loop with inductive loop for inductive power transfer to the coupled loop. So once the power is transferred from here, or energy is transferred from this loop, it first is retained here, the coupled loop, which then transfers it to the secondary stage. Port 2 is the secondary stage, while port 1 is our primary stage. So here is the input stage, the input excitation phase, where the power comes in. You can see the power, okay, where we let in power into the system, and the power, when energy flows into this, it produces the kind of energy, or when we let power in, it produces the kind of energy that we want to transfer wirelessly into this coupled loop. This loop helps to retain the energy and then be transferred to the secondary loop for further application. So we can transfer, and this is the distance, the loopy distance that we are using in modeling our equations, and so on and so forth. So this is the circuit of the inductive power transfer using a passive circuit, the normal passive circuit of inductor, passive circuit element of inductor and resistor, inductors and resistors to model and transfer energy across gap. Gap. Then the next one, these are the results, the simulation results. Here, the first one is the impedance against the frequency or versus the frequency between the series and parallel capacitor of the inductive power system. So if you look at this green one, is showing our capacitive output, and this blue one is showing our the parallel capacitor, and this green one is showing the series capacitor. Okay, so result obtained when we look at the impedance against the frequency output. And here is looking at the impedance versus frequency between the series and parallel inductor of the inductive system, between the series and parallel. So here you see these are for inductors, while these are for capacitors. Okay, these are for inductors, while these are for capacitor. In the case of inductive measurement, we can see that the parallel output, it's a better system when we consider output frequency with less impedance. With output frequency we let less impedance in the system. Okay, but while in the case of capacitive output, in both cases, both in series and parallel, the impedance is a very high value. The impedance value is a very high value. Okay, so this is another stage of the differentiation of the impedance versus the frequency in various load of the inductive power system. Here we looked at both the series inductive system and the parallel inductive system for this one, which is a better output when we're considering frequency. We get a better output when we use a parallel inductive system, but when we're looking at with less impedance, but when we're looking for impedance gain, then we'll be looking at series. We'll be looking at series in that regard. Now here is the normalized result, standardization and normalization of the impedance using some statistical method. Okay, the standardized impedance magnitude and frequency response is given here as one of the key outputs, and then the voltage and the current gains at various resonant frequencies are given. This first one is the standardized impedance output. Okay, a 3D measurement of the standardized impedance output. And then this second one is the voltage gain, the standardized voltage gain. Okay, the output measurement is of the standardized voltage gain in the system. Then this one is the third one for the 3D measurement, the current gain in the system. Now, these are result discussion. Now, what are the things we have come in terms with, or this research has be able to solve the results and the things achievement that this result key achievement that this research has been able to reach. One is the series resonant circuit minimum impedance, ideal for low impedance scenario. We'll be able to come into terms with the series resonant circuit, that whenever we have a series resonant circuit, we will have minimum impedance. We have minimum impedance which are ideal or useful for low impedance scenario. Any applications that require low impedance, our research has been able to use series circuit to model such applications for low impedance. There, in the case of parallel resonant circuits, which maximize the impedance, which maximize the use of the impedance, then this will be suitable for high impedance application measurement. Okay, so the research has looked at both low impedance characterization and high impedance characterization, and is able to harness this for the benefit of electronic telecommunication circuitry. Now, and also the research have achieved about greater or equal to 92% of efficiency of the entire system for the wire, for the energy transfer and the power transfer across board, and a low harmonics distortion has been achieved with just 0.2%. Okay, has been achieved in our simulations. Then the applications of this research. Where does this research find application? This research, we have tested it for a wireless energy transfer system. Without wire, we can transfer energy. You know, remember that in current power system, I think we need wireless energy transfer methodology, okay, to transfer at least energy across a short range of distance. So this research has modeled that characterization, ability to transfer power, energy across a short gap without the use of conventional wires. And then another applications of this is the inductive sensing in harsh environment. So this research is also a sensor. This develop resonant circuit is also a sensor. It's a transducer, as it were. It's able to sense harsh environment like pressure sensing. We've tested it for pressure sensing, and it's able to sense any available parameter that is very close to it in a short distance. Okay. Now the conclusions for this is we looked at the summary of conclusions that this research will be able to validate the proposed resonant circuit techniques for passive component characterization, which is the bane of the whole research. The big bane of the whole research is that we wanted to validate a resonant circuit that outweigh the current system, or that solves the current challenges in the current research, as it were, for passive component characterization, Okay. Then another achievement from this research is that we've assured accurate measurement and optimal energy transfer. We've been able to measure in a short gap. We'll be able to carry out measurement with optimum energy transfer without wastage, with up to over greater than 92% efficiency in the transfer system, energy transfer within the board. Now, the future work will probably be looking at ability to exploit scalability for higher power system. So one of the things we can do in the future is how to scale up this design, for a higher power transfer system, like we said in the power system, transmission, power generation, transmission and distribution. We need a system like this, a wireless system application like this, that can be interfaced with the current conventional power system to transfer energy across board wirelessly. Okay, this an ability to scale it up, and then to extend the applications to biomedical and industrial systems. So our next research in this area is to look at how we can employ or apply this sensory system, this transducer, into biomedical applications to solve probably the Parkinson's diseases uh, and in old people. So we want to use this. Our next phase of the research is to how we can use this resonance IQ system that we have in place, applying it in a biomedical application and in the industrial application. So these are our reference, some of the basic references that we've itemized here. And thank you for joining us. Once again, thank you for joining us.